Welcome to another installment of CCSD Living Environment. Today we're going to look at the properties of a population. One thing we need to consider is population density. So because we're talking about a population, we're referring to one specific species in one specific area. And when we talk about density in the case of populations, it's the size of the population in that given area. So for example, if we talk about a city would be more densely populated than, say, the countryside. Factors that affect population size could be density-dependent factors, things like food, space, and predators, or density-independent factors, something like extreme weather, drought, forest fire. Something of that nature would be what we would consider to be density-independent. So the density of your population, the number of your population in an area, is going to be dependent on the amount of food you have, the number of predators you have. That's a direct relationship. Whereas we don't have a drought every day, so your population wouldn't be as directly affected by that. When referring to populations, we need to consider something known as the carrying capacity. The carrying capacity is the average number of organisms of one species that an environment can support. So with a carrying capacity, what you have to keep in mind is the environment can support a certain number of organisms in that area. If your population has gone far above what can be supported in that environment, you're not going to be able to survive. So the carrying capacity, if it has been exceeded, the population will tend to go down. So a very simplistic graph to look at this would be if we have our X and Y axis and we have a stable, steady carrying capacity. Now, we're showing it here as a dashed line. That carrying capacity is saying this is how many of that organism we can support in this environment. If we go above, well, we can't support it anymore, so those organisms are going to start to die off. Well, if enough of them die off, then what's going to happen? They're going to be able to essentially produce more within that population, and it's going to go back up. And then again, there's too many, it goes back down. So you can see that we're kind of staying right around the carrying capacity with the size of the population. So how are those populations distributed? In other words, the placement of the individual members within a population throughout the habitat. Remember, your habitat is where you live. It is your environment. So the distribution of the organisms within that area is what we need to look at. Well, we have two options. They can be clumped, meaning they're all in one place. So it's kind of like if you ever watch little kids play sports, like soccer or basketball. Basically, it's the giant blob following the ball around the field because they're all clumped together, and you hear the coaches and the parents yelling, "You're all clumped up, you're all clumped up." Well, in the case of certain populations, they actually do clump, like a herd of elephants. They tend to be clumped. They're all distributed in one area. The other option is for something to be uniform. Now, when we think of uniform, we think of clothing, because that's your uniform, that's what you wear. Well, think about that from the perspective of our definition. Uniform is to spread out evenly. Okay, if everybody's wearing a uniform, everything is the same. It's spread out and things are relatively even. Now, granted, our clothes aren't spread out, but there's evenness to what you're wearing. Now, the thing you need to think about here, competition, generally speaking, will keep too many organisms from living in one place at one time. We know we can't have too many in one place. If I bring in large pizzas to feed everybody, and I only put down 2, and I've got a room of 30 kids, that's not enough to feed everybody. So competition is going to keep everyone from hanging out in that room. Now, if next door they have more pizzas, some of you are going to go hang out next door. Not necessarily because you prefer next door, but certainly because you have enough food. So what happens with that population? Well, what happens with the population is this idea of a growth rate. With the growth rate, it's the increase or decrease in the size of a population over a specific period of time. So we can set the time. We can say 10 years, like with the census. We can say 100 years. We could say 1,000 years. What has happened to that population within a set amount of time? That's the growth rate. The one factor that we need to consider is what we consider to be zero growth. Now, that doesn't mean that nothing happens. In the case of zero growth, your birth rate and your death rate are equal. So more members of the population are still being introduced into the environment, but the number coming in is equal to the number going out. And if that happens, you have zero growth. There is no population increase. So if we want to talk about population increase, or if we want to look at this idea of growth rates, what we need to look at are two different types of curves. Now for curves, we're referring to graphing. So again, you know we have our x and y axis. If we're going to talk about exponential growth is also known as a J-curve or an exponential curve. It occurs when there is no limit to the population size. Think about that for a minute. If you're living within an environment, you're living within an ecosystem, can there be unlimited growth to your population? Could that be supported forever? I'm hoping your answer to that question is no, it really can't. Every habitat has limits. So when the population increases beyond carrying capacity, available food and space decrease. If there's not enough food to feed everybody in that population, somebody's going to die, unfortunately. That's what happens. So this idea behind an exponential curve or a J-curve means our population is skyrocketing. It's going straight up. But think about that carrying capacity that we said is being maintained in one place. If you're maintaining your carrying capacity, the environment's saying, I can only support this many, but your population is shooting straight up in the air. We can't support that forever, whether it's humans or any other organism for that matter. So at that point, more organisms will die and the birth rate drops because the mothers that are having babies, granted they may be having the babies, but they can't support the babies. So if we consider birth rate just to be having the baby, well, if mom's not healthy enough to have the baby to begin with, she doesn't even get pregnant, so to speak. Or if there's not enough to support her once she is pregnant and she can't feed or nurture that, we can't continue. Now, it's always easy for us to talk about that with animals, but you have to kind of keep in mind plants too. If they don't have the right conditions, they're not going to be able to survive either. So what's our other option? Our other options would be something called the logistic curve or the S-curve. It shows the effect of a limiting factor. Now we've talked about a limiting factor to be something that kind of puts the brakes to a population and kind of has things hold tight. So if we have this S-curve and we have something that's kind of held the population in balance, held the population in check, are we going to grow out of control? Well, it could happen, anything could happen, but the chances are much less. And there's a really good chance that that population is going to be able to go on, continue, and reproduce. So if you look in your note packet with me for a minute, you have a couple of graphs. The first one is talking about human population. Now, I'm going to try to show you the graph so you can see where I'm looking at. I'm looking at this first one for human population. This goes back in the history of humans, and it goes back to the old Stone Age. So we're going back BC times, like a way long time ago. And you can see the human population is very small because your y-axis is dealing in billions of people. We weren't there. We weren't even at 1 billion. We were nowhere close. And we continue on until, I don't know, maybe about 1500 now, AD. And then you see there's this little dip in the population. Now below that, it kind of blows it up so you can look at that a little bit better. And it shows you that at about 1400, we had the Black Death, the bubonic plague. So when that came in, what did it do to human population? It really lowered our population, which wasn't very high to begin with. So there was a rebound to the population, it came back up, and we continued on until about the 1800s. And during the 1800s, that's when the Industrial Revolution took place. Now, if you don't remember, or if you haven't gotten there yet in your history classes, the Industrial Revolution was a huge boom with technology and medicine, and you kind of laugh at that and say, well, it's not the technology we have today. You're right, it's not, but it was way better than what they had a whole long time ago. So what happened with those populations is it started to boom, and it went up. And then you can see on there major scientific and medical advances. And the population keeps going. But notice we're still only at about 1 billion people, and that's maybe around, I don't know, 1950 or so. So from 1950-ish until now, 2014, we have had a major population explosion. Technology, medicine, and the fact that our birth rate far exceeds our death rate. So of the two curves we're talking about here, which one are we in? It's certainly that exponential curve, that J curve. So again, let's go back and think about that. Can that increase be supported forever? Probably not, unless some major things change. Now, if you turn the page, you're going to notice that there's a graph in there, and I'll show you the one I'm looking at here. Okay, the S and J curves together. And that shows you time on the x-axis and population on the y-axis. What it's showing you is what the J curve would look like and what the S curve would look like. And then you can also see where the carrying capacity is. In a perfect world, the S curve stays just below carrying capacity. So if my carrying capacity is here, my S curve is just below it. Just enough below that population will continue to thrive because of the effect of a limiting factor.